Okay, welcome back everyone. So today I'm going to be doing a video on Euler's great formula and a derivation of it. And the thing is, Euler's great formula is just, well, I can give it to you right now. It's actually just e to the I x, or theta as it's commonly written, is equal to cosine of x plus I sine of x. And this is truly beautiful. And from this, if you plug in x equals 0, you actually get one of the most beautiful formulas ever, right? Is it x equals 0? Actually, x equals pi, okay? You get one of the most beautiful formulas from that. You get e to the I pi plus 1 equals 0. Euler's identity, of course. So this is Euler's formula. And I'm about to prove it using the Maclaurin series of e to the x, sine of x, and cosine of x. So let's see how this is done. Okay, so, well, let's try to start listing out some terms of e to the x, sine of x, and cosine of x, and see if we can find a pattern using our Maclaurin series here. And for e to the x, it's actually really easy. We don't even have to find a pattern, because every derivative, the nth derivative of e to the x is literally e to the x. So we can figure out this. And at 0, it's always going to be 1. So we can directly find the series for this, which is just the sum, the Maclaurin series, from n equals 0 to infinity of x to the n over n factorial. So this is a very common series that you should know. For sine of x, and cosine of x, it's not as easy. We have to list out terms in order to help us actually work that out. But that's not that difficult. So start at n equals 0. 0th derivative at 0, okay? And what is that going to be? So sine of 0 is just 0, okay? So sine of 0 is just 0 over n factorial, that's over 0 factorial, that's still 0. And so the point is that the first term of sine of x, obviously the first term of sine of x in the Maclaurin series is 0. Second term, so we don't have to write anything, of course. Second term, so the derivative of sine of x is cosine of x, and plug in 0, we get 1 over 1 factorial is 1, and here we obviously get x, okay? Because x to the first power is x. Then, what is our next term? Well, the derivative of cosine of x is negative sine of x. So it's obvious that, well, for all the odd terms, or for all the even terms for that matter, this is always going to be 0. So let's just look at the odd terms. So, and that'll help us in actually finding the series representation of this, which will then help us to find the radius and convergence, which will then help us prove this. Okay, and that's why I'm saying this is part 1, because there's quite a bit to this process, of course. Okay, so the third term, our next odd term, right? Because we've shown that all our it's pretty obvious that all our even terms will result in a 0, because, let me just make this clear, because all our even terms will result in a plus or minus sine of x, which will always give us 0, and which will cancel out this whole term. So we're only looking at the even terms, okay? Yes. Sorry, we're only looking at the odd terms. I had a bit of a stupid brain freeze there. Okay, so the next derivative, the third derivative, so that's so that's just negative cosine of x, right? Right, so derivative of sine of x, cosine of x, derivative of cosine of x negative, negative sine of x, and then that's just negative cosine of x, yep. So we have negative 1 over, so minus 1 over 3 factorial, so that's just going to give x to the third over 3 factorial. And it's not a good idea to expand this out, because if we expand this stuff out, we're not gonna find our pattern as easily, okay? Next term. Okay, so that's just, we're only looking at the odd terms. So the fifth term here, or sorry, the n equals 5. Okay, let's see. So we're gonna have, obviously next to the fifth, we'll get a plus, because our next derivative is positive cosine. So plus x to the fifth over 5 factorial. And hopefully you see the pattern already. We're getting an alternating series here, okay? Alternating series, okay, and this goes on forever, of course. So how can we represent this as a series, in series notation? So we can't actually find the nth derivative, of course, so this formula is not really helpful to us right now. But there is a pretty obvious pattern, okay? We can think of this as x to the first power over 1 factorial minus plus, this is, yeah, probably just safe to leave that out. So, okay, well, we should start at 0, of course. N equals 0 to infinity of, okay, well, so we need, so we're raising, these are all odd numbers, right? And these are the same exact numbers. And we're going to be having some minus 1 to the n, right? Because all of the, we're going to have minus 1 because minus 1 to the n, because for the first term, it's positive. For the second term, it's negative, right? So that's basically the idea. So yeah, it's kind of hard to explain this with words because it seems so obvious to just do in your head. So you can just easily see that this is just going to be, well, I guess we can write this on the outside. n times 2 times x to the 2n plus 1, okay, over 2n plus 1 factorial. So there we go, that's our Maclaurin series for sine of x. And again, it's a Maclaurin series because it's centered at 0. So now time for cosine of x, and let's use a similar strategy, okay? And you'll see it's pretty similar to this, as you might assume. Okay, so let's use this to our advantage. So let's look at the first term. If we plug in 0, our first derivative, our 0th derivative is obviously cosine of x. Plug in 0, we get 1. So in other words, we should just get 1 for our first term. Okay, because plug that at 0, blah blah blah, that's just going to be 1, that's going to be 1, and that's 1, so it's just going to be 1. For our next term, we get negative sine of x. Okay? And that's 0. So now we're looking at a different pattern. All the odd terms in this series will cancel to 0. And using a similar strategy, you can see why that's the case. Okay, so now we just look at our even terms, right? So now let's look at n equals 2. N equals 2 gives us, well, the second derivative of this is, well, that's just going to be minus cosine of x. So at 0, that's just going to be minus 1. And we're just going to get minus x squared over 2 factorial. Okay? And we'll look at one more term, and then the series will become very obvious. Or the pattern, I should say. So plug in 4, we get plus x to the 4th power over 4 factorial. And we keep going as such. Again, it's an alternating series in the same fashion. And in this case where we have even powers, right? So this is just x to the 0 here. So you can think of this as x to the 0 over 1 factorial, or 0 factorial for that matter. So this is equal to, and you can easily see this again, this is going to be, well, we have negative 1 to the nth power as we had here, but this time we have even powers here. So we're going to have just 2 to the n, so 2 to the n over x to the 2n over 2n factorial. And you can verify that this works, okay? So these are our two series, and this is our e to the x series. So now we're all set, and let's see, okay, this has only been about 10 minutes long, so let's see if I can't, we can now find the radius of convergence for these things. So let's start off with the radius convergence of this. So let's see when this converges using the ratio test, okay? How could I give myself some extra room here? Okay, well, hopefully this will be fine. So I'm gonna lift the board up. Okay, whatever. So here, let's use the ratio test to our advantage. Ratio test. To show, you could use the root test, by the way, but I'm gonna use the ratio test. To see when this converges, okay? This is a power series, by the way. So, okay, so yeah, so let's use the ratio test. So as we know, we want to consider the limit as n goes to infinity of the absolute value of the n plus 1th term of a sub n, which is x to the n over n factorial. So we have x to the n plus 1 over n plus 1 factorial over x to the n over n factorial. And if this is, we want this to be less than 1 to converge, okay? And obviously it can't be negative because we have an absolute value here. Okay, so this is just going to be equal to, well, the limit as n goes to infinity of the absolute value of, okay, well, we get a lot of cancellation here. Notice that this cancels with this term here. And also we're left with an n plus 1 here because note that n plus 1 factorial equals n plus 1 times n factorial. Okay, so this will cancel, and we're just left with an n plus 1. Okay, well that's kind of nice, right? So all of that will cancel, and all in all we're just left with, well, x over n plus 1. So that's pretty nice. Okay, and note that this part, 1 over n plus 1 is always positive. We're only looking at on the range from n equals 0 to infinity. So this equals the limit as n goes to infinity of 1 over n plus 1 times absolute value of x. And this is actually just 0. So this limit will be 0. So 0 times absolute value of x. But wait, this is always going to be, no matter what value of x we plug in here, doesn't matter. It's always going to be 0, right? Because this is just going to be 0 times absolute value of x, which is always equal to 0. This is not an indeterminate form, okay? Because this has a definite value. So, well, what do you think that means? That actually means that this converges for all x. It literally converges for all x. It's always 0 for any x that you plug in here. So the radius of convergence is infinity. So here, for e to the x, it converges, well, the radius in convergence is infinity, and it converges on negative infinity to infinity. That's interval of convergence, okay? That's the interval of convergence, okay. So hopefully that's satisfying to you. Now let's go to the next to sine of x. Let's check that out. Also, I don't know why I always write sine of x like in front. For some reason, sine of x just pops into my mind first. Like, it's always first in line, but at least it's before cosine of x. I don't know. To me, it's just like something that should always be first, because, you know, the derivative of sine is cosine. I don't know, that might be why, who knows. Anyway, so let's use, again, I always try to see if we can use root test for this. Yeah, it wouldn't be a good idea here, obviously. So ratio test it is. And that might get a little tedious. So I might leave this to another video, but I'll at least start on it. Or at least the next video, of course. Ratio test for sine of x. So let's consider the limit as n goes to infinity of absolute value. This ugly thing. Okay. So note that, yeah, we have this negative factor on the outside here, but we can literally ignore it since we have our absolute value. It's always going to be 1, so that's not going to change anything, so we can just ignore it here in this case. So we have x to the 2 times n plus 1 over 2 times n plus 1 factorial over x to the 2n plus 1 over 2n plus 1 factorial. A bit more tedious, of course, but let's see if we can simplify this. Okay, so this is, let's first expand these. We get limit as n goes to infinity of absolute value of x to the 2n plus 3 over 2n plus 3 factorial over x to the 2n plus 1 over 2n plus 1 factorial. Okay. So this will actually, there's quite a bit which will cancel. Here this will cancel, and here we're going to be left with, we're just going to be left with x squared. Here, this will cancel. Here we're going to be left with the factor of, you kind of have to think about this. So 2n plus 3 factorial equals 2n plus 3 times 2n plus 2 times 2n plus 1, etc. But notice that this segment is just going to be 2n plus 1 factorial. This will cancel with that, and we're just left with a factor of this. So we're just left with that, basically. So again, we're left with a pretty nice cancellation here. So limit as n goes to infinity of absolute value of x squared. This is always going to be positive or 0, of course, so we'll bring that out in a second. And on the denominator, we're going to be left with 2n plus 3 times 2n plus 2. And already it's pretty easy to see that we can just, remove the absolute value. This is always positive. And this denominator is just going to be, if you pull that out, the limit of that is 0, so this equals 0 times x squared, which is always 0. So again, no matter what, this is always going to be less than 1. Less than 1 for all x. Okay? So thus the radius of convergence is infinity again, which tells us that it works for all x. This converges. Our sine converges for all x. So And so that implies this gives us that our r is infinity, and our interval of convergence is negative infinity to infinity. So I'll leave this cosine one maybe to an exercise to you, the viewer, because it uses the same exact process, and I'm sure you can work this out. In fact, I encourage you to actually try out the root test. That might be an interesting exercise there. So hopefully enjoy that video, and I'll see you in the next one, where we actually begin the proof, okay? Which is going to be much shorter than this. And again, I'm leaving this to you as an exercise to show that the radius and convergence here is infinity. So hopefully you had a nice day, and goodbye.